Hello everyone. In this mini lecture, we are going to talk about experiment reinforced concrete. Here are the objectives of this experiment. From this experiment, you will learn the basics of concrete and its ingredient. You will learn the water-cement ratio and how it relates to the compressive strength of concrete. You will learn workability as the most important fresh property of concrete and how to use a sample test to measure workability. You will learn 3-to-1 method for a quick and easy concrete mixture design. You will also learn basic concept of steel reinforced concrete. Okay, if you are a mechanical engineer or biosystem engineer, you may wonder why you need to learn concrete, because concrete is apparently civil engineering stuff. You want to learn about concrete because concrete is a very important material. It is the second most commonly used material in the world, next to water. There are about 10 billion tons of concrete being produced per year. The reason why concrete is widely used and why this material is so great is that it is a very versatile material that can be formed into any shape at its fresh state. Okay. It is also, once it gets hardened, it's also a material that it can be also an excellent structural material because it has high strength and long durability. Because of this, concrete has been widely used in bridges and buildings because that can make the structure last very long. And there are 4 major ingredients of concrete. These are water, Portland cement, sand, and aggregate. Among these ingredients, Portland cement is the most important one in modern concrete. So Portland cement, what is Portland cement? Okay, Portland cement was first made by this person, Josephine Aspdin, in England about 19th century by burning powdered limestone and clay in his kitchen stove. Okay, and why Portland cement is important? Because Portland cement is the most widely used hydraulic cement in the world. What is hydraulic cement? Hydraulic cement is defined as a cement binder that is not dissolvable in water, so that capable of withstand various weather and harsh environment. In contrast, non-hydraulic cement, such as the lime cement from the ancient Egypt, is dissolvable in water. That means if there is a rain, the structure may not be safe. The first person that come out using hydraulic cement are from ancient Roman. They use volcanic ash as a hydraulic cement. But the problem of volcanic ash is it's not exists everywhere. So Portland cement solves this problem. It can be mass-produced almost anywhere in the world. Another advantage of Portland cement is that it can gain strength much quicker than the volcanic ash cement. Typically, it takes like 7 days to get some sufficient strength for testing, but for the volcanic ash cement, it usually takes several months. How Portland cement works? The major reaction of Portland cement is the hydration reaction that reacts water to form hydration product of calcium silicon hydrate, or CSH. This material will form on the surface of cement grain. CSH is the bonding material that gives concrete strength. That's because it has a morphology I show here, has a morphology with high surface area that is similar to silicon. This high surface area will produce a van der Waals force that can give concrete strength. The strength of concrete is highly dependent on water cement ratio, which is directly correlated to the proximity of cement grain. That's the average distance between each individual grain. Typically, the lower water cement ratio gives a higher compressive strength, where I show a diagram to compare the case of low water cement ratio and high water cement ratio. And the lower the water cement ratio, like in this case, the closer and the individual grain get packed together, which will increase the binder force between the particle, as I mentioned earlier. It also will reduce the volume of the voids. That's why lower water cement ratio typically generate high compressive strength. Concrete mixture design, finding the right proportion of ingredient is the key to build high-quality concrete. This process is called concrete mixture design, which usually referred to a standard procedure in the manual of American Concrete Institute 221. If you're interested, you can search online the standard ASI 221 manual. You can find the step of find the right proportion of the ingredient. But here, we are going to use the classic and simple 3-to-1 method. By rule of thumb, that means we need 3 weight proportion of aggregate, and we use 3 kg, 2 weight proportion of sand, 2 kg, and a 1 weight proportion of cement or PC, that's 1 kg, with enough water. First, we will try water as 0.5 kg, then we'll keep adding water until we find the right amount of water. There are 2 major properties we care about concrete in this experiment. The first one is strength, or compressive strength, which is directly related to the water thermal ratio. And the second property is the workability, which is directly related to the amount of water we're adding to the mix. The more water, the higher the workability, but that will reduce the strength. The compressive strength of concrete is determined by performing compressive tests on a concrete cylinder sample. In this experiment, you will make a few concrete cylinders and you will perform compressive tests in week 3. The second property we care about is the workability of concrete. The workability refers to how easy freshly mixed concrete can be placed, consolidated, and finished with minimum loss of homogeneity. It is very important in the construction field. Workability is determined by performing a slump test. Here I show a brief step of how to perform a slump test in our experiment. Here I have a plastic cone with the opening at top. I fill this cone by 3 layers of concrete, with each layer well compared by rolling 15 times. Then I take off the cap to let the concrete inside to sleep. The height reduced by slipping from the cone is that we measure as a slump. Reinforced concrete. Although concrete is pretty strong in compression, but it is also known as a weak material in tension, and that's why in practice, reinforced steel bar often added to take the tensile stress. That's why in construction field, you see many reinforced concrete, and in many cases, for the concrete structure, you can see concrete works with steel. In this experiment, we are going to cast a concrete beam with the steel bar reinforcement at the bottom. That's because the bottom is where the tensile stress applied. Here is the overview of the procedure of the experiment. First, you weigh 2 batches of ingredient material and perform hand mix to get an initial mix of concrete. Then you're going to perform a slump test to see the initial slump. Most likely, your slump won't be great. For example, I show example here, the slump equal to 0. That is the height of the concrete after I remove the cup is almost the same as the cup itself. You will also make a cylinder for this initial mix. Then you're going to keep adding water at 100 grams per step, and you do a hand mix and perform a slump test. And you keep adding water until the mix reaches a good slump. Then the good slump will look something like this. I call it final slump. As you can see, the concrete collapse, slip, and a slump of about 2 inches. Okay. Then you're going to make a cylinder for this mix. Okay. Once you do this, you're going to use this material to cast beam. Because you have 2 batch material, 1 batch you're going to cast a beam without reinforced steel, other batch you're going to cast beam with reinforced steel. Then in week 3, we are going to perform compressive tests on these 2 cylinders, and also we are going to perform the bending test on these 2 beams. That's it. Good luck for the experiment.